אז הנושא של היום, זה במקום לדבר על משוואות דיפרנציאליות, אנחנו נפנה לנושא שהוא הרבה יותר פשוט, עקרונית, אבל נראה שאותם תופעות מוזרות של כאוס ודברים כאלו קיימים אפילו במערכת הכי פשוטה שיש, המערכות של maps. אז map זה משהו פשוט, יש פונקציה f, כן, ו-f(xn פלוס 1) זה f של xn. Oh, what? I'm speaking to you. I don't even know. All right, so yes, we're talking about maps, and we have the map is defined by some function f, which takes xn, and you get xn plus 1, and then the next value of the time series, so you generate a time series this way, a whole series of x's, and very good. So now, and of course, just like with a differential equation, we had fixed points where, right, we had x dot was x f of x, and then f had to vanish, and that was a fixed point or a stationary point, whatever. Here a fixed point is when f of x, kochavit, x star equals x star. Right, that is a fixed point, because then you get stuck at x star. Right? If you start with x star, then the next iteration is x star again, and x star again, and x star again, so that's a fixed point. All right, now, and then you can ask the same question like we asked with differential equations. What about stability? All right, once you identify the fixed points of the map, the next question is, are they stable or not? Now, stable again is slightly different. It's the same linearization procedure, but because this is, you'll see that there's, so what does it mean? So if we start out not at x star, but we have x star, xn, say, is x star plus some delta n, right? And then the question is, what's the story of, so then xx plus 1, which is xn plus x star, xn plus 1 is, by definition, x star plus delta n plus 1, that defines delta n plus 1, and this is supposed to be equal to f of xn, which is x star plus delta n, but since delta n is small, we can Taylor expand, and we get f of x star plus f prime of x star times delta n. But f of x star, because it's a fixed point, is x star, and so this is x star plus f prime of x star delta n. And then the x stars go away, and leaving us with delta n plus 1. The recursion for delta is delta n plus 1 is f prime, to linear order, is f prime of x star times delta n. And now, the question is, how big is this f prime of x star? If it's 2, then delta gets bigger by a factor of 2 every time. If it's a half, it gets smaller. So stable is when the stable means that the absolute value of f prime of x star is less than 1. That's what it means to be stable, because then it contracts. Delta gets smaller each time in magnitude and eventually winds up being 0. Whereas if it's greater than 1, it blows up and gets big. Right? So, and if f prime is negative, but between 0 and minus 1, then it oscillates around the fixed point, but it's like spirals. It's the discrete version of spiraling into the fixed point, if you will. Okay? So that's all very trivial.
It's similar to like numerical methods, right?
Exactly, right. This is exactly.
It's an iterative method.
Right.
It's like an iterative.
How you do with
What?
addition?
What's the problem?
What? Yes.
This?
Yes.
It's called Taylor. F of a function, f of x, delta small. So we expand the linear order. Right? So this is not equal, this is approximately equal. And then there's of course delta n squared, but delta n squared is super small.
Okay.
Right? Okay. And then a crucial geometrical tool when talking about maps is the following exercise. You draw the line. This is xn plus 1, xn plus 1 is the function of xn, i.e., so here's the map, say. Let's imagine the map looked like that. This is f. Right? And now you start at this x here. Right? So what is it? The question is, use this picture to generate the next x. Well, f of x n is this point over here. Right? And now you're supposed to feed that into, you're supposed to calculate f of this point. Well, the way to do that is go over here and then go down. Excuse me, so you go over here, and this has this x, this is, because the height here, right, this is f of x1. Right, this is x1. This is f of x1. Now, this value of x is when x equals f of x1, right? So that's exactly, which is x2, so this is x2, and then you go up to here, that's f of x2, and then you do the same thing, you go to the diagonal, this is f of x2 here, and now this is x3, and you go here, and you go here, and you go there, and you go wherever you go. That's called a cobweb diagram, technical term, right? Like the spider web. Yeah.
Newton-Raphson, right?
Yeah, it's Newton-Raphson is a map, right? Mm-hmm. And so yes, it's this Newton-Raphson is a kind of map, but it's hopefully not chaotic, right? Because if it was, that means that Newton-Raphson doesn't work.
Yeah.
I think in the complex plane you can generate like a fractal using...
Yeah, right. No, you can, and right. When Newton-Raphson doesn't work, it can be a
collection.
It can be a chaotic map, right? That's not where you want to be when you're solving nonlinear equations,
No,
right?
the fractal is created by looking at where the point...
Yeah, right. Yes, exactly. Yes. When you look at the Bayesian retraction of which points go where and all that stuff. Well, okay. So that's all very simple. And so, for example, if you had the map, if f of x was sine x, for example, right? So here's x equals y. And sine x, what does sine x do? It has the same slope here, but then it goes like this, right? That's sine x. Right? And now, say we started here. We started at that x, right? Excuse me. We started at this x. We'd go here and then down, and then we'd go down and down and down and down, and we'd converge to 0. Right? Now, why is that? Because in fact, now here, even though sine x actually is to linear order has derivative 1. The derivative of sine is cosine. Cosine of 0 is 1. Nevertheless, this is non-linearly, x is a non-linearly stable point. Linearly, it's marginal, but non-linearly because, right, if x is small, then xn plus 1, so delta n plus 1 is delta n minus delta n cubed over 6. So you see that it's getting smaller and smaller. But the picture sort of...
If it's getting smaller and smaller, it is stable, no?
Right, so this is stable. But it's not linearly stable, it's non-linearly stable because, you see, here, that would say it didn't change at all.
Yes, so you see.
Right, so you need the nonlinear term to actually get you where you need to go. But the picture does it automatically. Right? That's the nice thing about the picture. Okay, so very good. And,
So it
yeah?
will not diverge in the picture.
No, it starts here, it
You
converges
start
to
there.
0.
Okay, okay. You start there.
It
Yes.
started here and it converges to 0. Right? Now, let's talk about another case. What happens if we have another complicated function? What happens if f is cosine x? Right? Cosine x, so here's our x equals y. Cosine x looks something like that. Right? So what happens here? Let's imagine we start at 0. We go up to here. We go across. We go down. We go here. We go here. We go there. 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 And we're spiraling in, right? And because the solution of the fixed point is the solution of the equation cosine x equals x, which is some number. It's something like 0.739 approximately, and the derivative f prime of x star is minus sine of x star, right? And now I don't know what the sign of that number is, but I know that it's less than 1 in absolute magnitude, because that much I learned. And it's got a negative sign because sine is positive between 0 and that, right? And therefore...
You also calculate it because you know the cosine.
Yeah, but I don't have to calculate, right? I mean, the point is it's a negative number less than 1, so it's stable, and it oscillates around. So it spirals in to the fixed point, which is exactly what we saw for the picture. So the picture does.
Why it's stable?
Because in magnitude, this number is less than 1 in magnitude. Right? Because sine is less than 1. Okay. Now, the most famous map of all time, and the sort of the start of the industry of maps in one way. So maps had two starting points. One was the Lorentz map we saw last week, which showed that somehow the Lorentz system could be reduced approximately to a discrete map. But the other historical key map in the world of maps was what's called the logistic map, which is the following map: f of x is r times x times 1 minus x. Now, this is like the logistic. There's a logistic differential equation. The logistic differential equation says that x dot is, say, r x minus x squared over something, whatever. Okay, doesn't matter. And so it's if you write down that x is n plus 1 minus xn, right? And so if you discretize use Euler, right, to generate a discrete update scheme for x, right? Well, this is what you get. You get a constant, you get xn plus 1 equals xn. Well, let's don't call this r, let's call that alpha. Is xn times 1 plus alpha minus xn squared over k. Well, that's, roughly speaking, that, right? And so the one of the most famous this equation is used to describe the growth of populations, which is that the x dot is x dot is that. Excuse me, here that's right. X dot is that. It says the population, when it's small, grows exponentially, but then at some point it has to saturate because there's a finite amount of food, there's a finite amount of whatever, and so you can't support an infinite population. You get Malthusian catastrophe.
It's also applied for viruses.
It's applied to everything under the sun. Yes, right. But yes, it's viruses and everything that grows and multiplies and then has to saturate because nothing can grow forever. So the point is that if you're right. So now we told you if you take the course in numerical analysis, you're told that in fact there's a dt here, right? I mean, xn is this, there should be a dt here and a dt here, right?
Yes.
And we told you to take, you're not allowed to take tt too big, because if you do, you get problems. Well, the study of logistic map is in some sense what happens when you're an idiot and you take dt to be too big.
Yeah, you here dt is just 1.
Right, that's too big. Right.
Yeah.
So we'll see. All right, we'll see. Yeah, depends on. And the guy who was studying this was a guy who was a former physicist who turned to work in population dynamics, and his name is one of the more famous names out there, Robert May. So he was playing with the logistic map, right? Because it's a natural thing to talk about in population dynamics, because what happens is you don't measure the number of birds every 10 seconds. That's a sort of dumb thing to do. You measure at best like once a year, maybe once a quarter, maybe. But basically once, because, like the sheep, they reproduce every spring. And so if you want to track the number of sheep growing, you look at the number of sheep from year to year, and then you plot it up, and you come up with a rule like this saying, well, if there are a small amount of sheep or whatever they are, there's more next year. And if there are too many, then they die off, and you get...
Dynamics does not include the foxes.
Right, this is without the fox. This is just the sheep by them. This is just the sheep by themselves. They have a limiting dynamics because there's a limited amount of grass that they can eat. And so if the population is too high, they overgraze, they die off, blah, blah, very sad. And so it was natural for people who work in ecology to say, we don't like differential equations. Anyway, that's hard math, right? Right? What we have, the data we need to fit to in the end of the day is a discrete set of data points. So let's use a map to describe what's going on. And then, so Robert May was playing with it, and he said, but this is a problem because this map does weird things, he discovered. Yes?
Why is it a X word by like K and not
There's a whatever, yeah, you can put the alpha here too if you want. It doesn't matter. I mean, it just changes the... I didn't tell you what K was, so it's alpha over K, it's the same thing, right? It's just a number.
K alpha is constant?
Yeah, they're constants, right? Alpha is the growth rate, and K, when you write the alpha here, K is the carrying capacity. And of course, the word carrying starts with a C, so that's why you call it K, because C and K, carrying, it sounds like a K, so that's good enough, right? Okay, now, so we are going to spend the rest of the time we have today talking about our friend, the logistic map. Because there's an infinite amount to say about this stupid logistic map. You would think that there's nothing simpler in the universe. And the whole point that Robert May, after spending like a year playing with this, wrote a paper which became famous because you take this simple equation like...
and it's applied to everything.
And that's applied to everything, and all of a sudden, it does crazy stuff.
We've assumed that Fox has an egg job.
Right. Yes, assuming foxes are negative. Okay, so now, fixed points of this map. F of x equals x, right? So, it's very simple. There's a fixed point at x equals 2, so you have, therefore, x equals rx 1 minus x. So one solution is x equals 0, right? And the other solution is that x equals 1 over r, 1 minus 1 over r. Yes. Right? Because if x equals 1 minus 1 over r, then 1 minus that is 1 over r times r is 1, and we got a solution. Right? So there are two solutions. Now, obviously, if r is less than 1, then this solution is negative, and we call that unphysical, right? If you're an ecologist, at least, you call that unphysical, right? If you're a mathematician, you say, in fact, this is sort of like a transcritical thing, because there are two solutions that come together when r equals, right, you have the two solutions here and there. This one at x equals 0, and this one goes here, and they cross at when r equals 0, and therefore it's like a transcritical bifurcation, if you will. All right. Now, so with stability of r equals 0 of this thing, with the stability f prime is r times x minus x squared. Derivative is 1 minus 2x. Right? So when x equals 0, so f prime of 0 is r. So this is stable if r is less than 1. Right? Because the derivative is stable when the derivative in magnitude is less than 1.
Wait, why is 0 x equal to 1 minus r, 1 over r?
Solve this equation.
It's x equal to 1.
All right? X equals rx, 1 minus x. I got rid of this. This is the 1 now. And, right? Okay. So, the origin is stable if r is less than 1, because then the number of people shrinks every year. So if I started out with 5 people or whatever, next year I'd have, 5/2 of a person, and then 5/4 of a person, and so forth and so on, and I'd wind up with nothing. Right? Which shows you how useful these models are when talking about sheep. Right? Okay. Fine. And then there's the other. So, given the analogy to a transcritical bifurcation, and this is unstable, of course, the origin is unstable if r is greater than 1. And now the other fixed point, this one, right, is stable when, well, okay, let's put it in. That if we put in that, so f prime of 1 minus 1 over r, right, is r times 1 minus 2 minus 2 over r, right?
Plus 2 over r, no?
What?
Wouldn't it be plus 2 over r?
Yeah, if I know how to do math, but that would, right? So now, this is r times 2 over r is 2. This is minus 1, so that's 2 minus r. Right? Did I do that right?
Yeah.
Yes. So when r is 1, it's marginal, right? Because that's when this thing, right? That's exactly when these two cases cross, right? The 0 changes stability at r equals 1, and it was unstable before r equals 1, and now has become stable. So for r greater than 1, it's stable, but r has to be less than 3, because if r is 2, this is 0. If r is 3, it's minus 1, right? And then the magnitude of f prime is 1 again, and if r is anything bigger than 3, it's like minus 1.3. The magnitude is greater than 1. So r has to be between 1 and 3 for it to be stable. Is that clear? All right. And now what happens beyond r equals 3? So you go to the computer and you do it, right? So you can do that. So you can actually, okay. So what it turns out is you get, when r is slightly greater than 3, say r is 3.1, say, what happens is instead of having a fixed point, you have now it oscillates. Up, down, up, down, up, down. So there's a period to solution. All right? That's what you see. Now you can derive that, and one way to derive that is to ask what happens just beyond 3. Right? If r is 3 plus epsilon, then we can try to write down the dynamics of, right? And we say that x is, okay, when r is 3, the fixed point, right? When r is 3, whereas the fixed point is 1 minus 1 over 3, that is 2/3, right? So say that x is 2/3 plus delta. So r is 3 plus epsilon, and x is 2/3 plus delta, right? xn, if you will, right? Is 2/3 plus delta. And okay, right, and then you can work out that actually. All right, so okay, what? Let's explain it. That's okay. Let's assume we have a period 2 solution. Not that it's easier to. So one way to understand the period 2 solution is that f of x1 is x2. Well, this is traditionally called p. It's called that q, and then f of q. Right? If this is p, then this is q, and f of q is back to p. So we have two things, p and q, and f of p is q, and p is f of q. Right? And, all right, which means that p is f of q, but q is f of p. Right? So if you have a period 2 solution, then if you apply f twice, you get back to the same thing. So p is a fixed point of f of f. So which is true. If you're a mathematician, you write that way. All right? F composed with f. Now.
How do you say 2 is a period?
Oh, well, okay. So I cheated because I actually went to the computer and I looked at it, right? And that's what.
It doesn't have to be true for every other cases, right? For other cases.
There is a no. So there is a. So it relaxes to a period 2 solution. It doesn't. If you start out with a random initial condition, what happens is and so you start out with. You start out with r equals 3.1, say, and now you pick a random initial condition, and what you'll find is that after the transient dies away, you get up, down, up, down, up, down, up, down. So you see that there's a period 2. It converges to a period 2 solution. That's what the computer tells you, right? And if it's true, yeah.
No. And I was asking about another thing. So if you want to finish.
No, all right.
About it matters the order of epsilon, or we can make the change as big as we want.
No, because if you make it too big, then things get more complicated.
But how is too big?
Well, there you have to give us time, man. Hey, the evening is young, right? Okay. So what we have to look at is f of p. So okay. So in fact, you can now. So what does f of first of all? What does f of p look like? It's r times x, right? But x is f of p, which is r. So it's r times x times 1 minus x. Times 1 minus rx 1 minus x. This is f composed with f. Right? I take it's r times, right? This is f, and then 1 minus r times f x 1. This is f. Okay. So which is in fact a quartic polynomial, and it looks something like. It's symmetric around the half because the original thing is symmetric around the half, right? The original map has a maximum at a half and goes from 0 to 1, right? So this thing looks like that. Yeah.
That's only for r bigger than 3.
That's right, for r bigger than 3.
For r lower,
Well, I mean,
it looks kind of different.
Let's see. Yeah.
According to that was yes.
Yeah.
Right. Right. There's only because the solution. Right. Because what happens then is it looks something like probably.
Like a kind of parabola.
Or something like that.
Yeah,
And the point is that there's only one non-trivial fixed point here, and as these peaks get higher, as you increase r, these peaks get higher, and then in fact this line has
Three intersections.
it has 3 intersections. This one, and this one. Right. And in fact, this is the unstable fixed point now. This is an unstable fixed point because it's got a large slope, right? And this one has a small slope, and this has a small slope, and the period 2 solution is going back and forth between here and here, which maybe we can see. I can't guarantee it. Let's see. You go here. You go here. So if you go here, you go. Yeah, my picture's not good enough to do this nonsense anymore. All right. Anyway, there are now 4 fixed points of f of p. All right, f of f has 4 fixed points. At 0, that's still a fixed point because it was a fixed point before, and so therefore your fixed point. Staying a fixed point when you apply f twice, right? This was a fixed point. This one was a fixed point before. This is the 1 minus whatever 1 over r, right? It's and then these 2 are the new fixed points which have been born when r crosses 3, right? And in fact, it's like, if you will, a pitchfork bifurcation. It's like a pitchfork bifurcation. We had a stable fixed point, namely the 1 minus 1 over r, and then we increase the parameter, and all of a sudden we have now, in that vicinity, we have 3 fixed points, the middle one being unstable, and now, however, so it's like it's actually more like a hot bifurcation. It's really like more like a supercritical hot bifurcation, because you get an oscillating solution, if you will. Yeah.
It didn't work that to the drawing with doing the steps because you plotted the steps of f of x, not the f of x.
Right. Yes. Right. Yes. Exactly. True. And don't ask me to. Okay. All right. So, in fact, you can actually take these equations and take this equation and look for the fixed points of this map, right? In fact, it's not that, it looks terrible because it's a quartic equation, you can't solve a quartic, but we know 2 solutions. We know that x equals 0 is a solution, right? Because there's an x here, right? So now it's only a cubic. We know there's another solution, which is this solution, right? And now it's a quadratic, and so therefore you only have to solve a quadratic, and when all is said and done, you can write down what the solution is. And did I manage to do that? I wrote it down. The question is, yes. Yes, it's r plus pq is r plus 1 plus minus the square root of r minus 3, r plus 1, all over 2r. That's the solution. Because it's a solution with quadratic, so you can do it. Okay, and notice that, of course, this solution doesn't exist in the real world if r is less than 3. So that makes perfect sense. So that structure sort of had to be there. Right? Okay. Now, okay. And now the question is, what is the stability of such a thing? Right? I mean, if I made the claim that if we start off slightly off of P, if we are at P, we go to Q, and Q goes to P, and P goes to Q, and Q. But what if we're at P plus something? Right? What happens then? Well, so to do that, you have to look at, right, if I start out with P plus delta, right, then I have to do F of this, right? And this gives me what? This gives me F of P plus F prime of P times delta. But F of P is Q, right? And now I have to take F of that. So I have to take F of Q plus F prime of P delta, which is F of Q, right, which is P, plus delta F prime of P times F prime of Q. Which is a very nice result. All right. Is there a problem? No. Okay. So therefore, F prime of P is F prime, as we know, is R times 1 minus 2P. This is R times 1 minus 2Q, right? And so therefore, F prime is this times delta. Is this. And the question is whether this is bigger than or less than 1 in absolute magnitude. If it's less than 1 in absolute magnitude, then this period 2 solution is stable. All right? And so in fact, there's one value when P is a half, in fact, this is 0, that's called being superstable when the derivative vanishes, because then there's no change to linear order. But so you start, and so what happens is at the bifurcation point, we know that this is equal to 1 because that was an instability of, then the solutions all glomp onto each other, right? But at R equals 3, this solution is at the same point, so everything is at 2/3, right? And so at 2/3, we should get that this, right? At 2/3, we should get that 1 minus 2P is 1 minus 4/3. Did I do that right? Yeah, 1 minus, that's 2/3, so that's 1 minus 4/3. Is 1 minus 4/3 is minus 1/3, that's right. So we get 3 times minus 1/3, 3 times minus 1/3, and that equals 1. So F prime at the bifurcation is 1 because that's the point of instability. That's the critical point, right? That's exactly where the bifurcation sits in. And then as R gets bigger, then in fact this number gets smaller than 1, goes to 0 at P equals a half, or Q equals a half, whichever one. If you call P the smaller one, then it's a P equals a half, right? Because 1 is the smaller or bigger. So, and then what happens is you make R bigger and bigger, and at some point, in fact, this goes to minus 1. What happens then? The same story. And now, each one of these points, right, in our up, down, we had up, down, up, down, up, down, up, down, except that now each one splits into 2, and what you get is up is you get very far up, down, very far up, medium up, medium down, very far up, very far down, very far up, boom, boom. And so you get boom, 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 boom. This is a period 4 solution.
Again, what?
What?
I just understand boom, boom, boom.
So each, just like when we had this thing, right? The fixed point became two points that oscillate between them, right? Now we have that solution which is 2 points oscillating, but each point now you get each one oscillates. So you go from here, but the higher one of this, to this one, the lower one of that. You go back to here, but now it's the lower one of that, and that gives you the higher one of that, and then you go back, the whole story starts again, you get a period 4. So there is a period 4 solution above some critical value of R, which is bigger than 3.
And there's a period of 5.
No. We went from period 1 to period 2 to period 4. What's the next in that series? 1, 2, 4.
6.
No, that's
1,
0, 2,
2,
4, 6. 1, 2, 4, 8. Exactly.
Yeah, but there will be also a 6, but not new ones.
No, the next one is 16.
Yeah,
The next one is 32.
I'm asking if there is a solution to the 2 period. There will be a solution for the 6 period.
Well, there will be, but we're not there yet. This one, what happened? I'm telling you what happened to the period 2 solution. It becomes a period 4 solution. What happens to the period 4 solution if you just keep slowly dialing up R? It becomes a period 8 solution. The period 8 solution, when you dial up R a little bit, becomes a period 16, 32, 64.
Stable one or
What?
A stable one or not?
Stable. Right. At the point, it's born when it's marginally stable, becomes super stable, and then goes unstable. And then at that point, you're period twice the period, and the whole story starts again and again and again and again.
And that happened for R that is big enough.
Well, so what are the R's?
Yeah, you need to find the R's.
You need to find the R's, right? And so.
But if R is big enough, it will apply, right?
R.
Big enough or small enough?
Did I not have my piece of paper here that has all my cheat notes? Had that written down. There they are. Okay. Yes. So
you need new condition for R to.
So the conditions for R the period 4 is born. So the period 2 is born at 3. We said, right?
Mm-hmm.
R equals 3. This is the period.
R less than 1 is not physical or something like that.
R. That's dumb. That's dead. That's dead, man. Right? This is the period 2. So we have the period 1 solution happens at 1 if you want, right? And then that happens at 1, and then are the 2 at 3, the 4 at, drum roll please, 3.449 something or other. The period 8 solution is born at 3.5644 or something. The period 16 solution is born at 3.5. 3.5449, 3.5644.
It's monotonic.
30. Of course, it's monotonic. 3.56879, and then ... to infinity, and it becomes you get an infinite period solution at 3.569946.
What happened after this?
That's an excellent question. The story goes that Robert May posted on the board of, on some chalkboard out of his office, what the hell happens after R infinity, right? And the answer is, drum roll please.
What is R infinity?
Where the period becomes after the infinite number of these
infinity plus 1.
Period doubling transitions.
Okay.
Right? And then you make it even bigger. You can just make it slightly bigger. What happens at R equals 3.57?
Okay.
All right? So we need a language, we need a graphical language to be able to discuss this. So what we're going to do is do the following plot. Here is R and here is X's. What does that mean? We pick an R. And now we pick a random initial condition. Run the map for 1,000 times so we forget what the initial condition was. We're looking at we let the transient die out, just 2 seconds. We let the transient die out. And then we have the computer plot all the values of X. And this was a period 2 solution, so only 2 values of X. And you just, right? And now we make R this big. And now, again, there's only, say, 2 values of X. And then we hit our magic number of 3.449. And now what happens is we have this, that, this, that. This point split into 2. Right? And now we go here, and now we have 8 points because this split into 2, and this split into 2, and this split into 2, and this split into 2. Right?
Until it will be.
And then and now, so now you understand the picture. You can now understand what happens for. So here is
It's a
the
fractal,
period 2
right?
solution. Here's the period 2 solution. That's right. This is the period 4 solution. Here's the period 8 solution. Right? It gets harder to see. There's a 16 solution here, but it's just 2 seconds. It's very hard to see, right? And then all of a sudden, it's a mess. We have a technical name for messes. They're called chaos. This is chaos. That past R infinity, the system is chaotic, but not always chaotic, because you see here for this value of R, there's a period 3 solution. And here, if you look closely, which you can't because it's very hard to see, there's a period 5 solution here. And in fact, here there's also a period 6 solution, and a period 12 solution, and a period 24 solution, and a period 48 solution, blah, 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 whatever, you can do that. Here, this is a 5, 10, 20, 40, whatever. This is a period 6 solution, 6, 12, 24, whatever, whatever. So,
It's black.
what?
Drawing.
Well, I mean, it is in between these windows. So there are the windows of sort of normal behavior. There are these what are called periodic windows. In between, it's a density. I mean, every point is in principle. It's really a Cantor set. Now, I can't say that every point is filled up because they're holes. There are an infinite number of holes, and they're holes of all sizes, and because this is like a fractal type of thing.
Yeah, but why it's colored black? Why?
Because the printer has finite resolution, man.
No, I don't understand why.
There are so many
Why
points.
there's
There-
supposed to be a lot of points? You say 5.
Because it's chaotic, which means that it basically goes over the whole range between 0 and 1. Or not between 0 and 1, between 0.3 and 0.7.
Okay.
And it basically covers that whole range.
And why you connect them with a line?
There's no connecting with lines. This is what you get. Go to the
Okay.
computer, run the experiment. This is
okay,
what you
okay,
get.
Okay.
I'm just plotting the points for each value of R, and you step along an R, with some small delta R.
Yes.
And for each value of R, you just run off 1,000 points throw them away, and then you just plot the points, and they do what they do. And if it's periodic, you get a nice set of 2 points or 4 points or whatever.
Just cuts an end.
What?
There is no fixed point for R bigger than R infinity, or something like that.
Huh? I didn't understand the question.
After the.
This is
value
R
of
infinity is
R
right here. This is R infinity. That's there. And here, if you want to see a blow up of the picture, this is a blow up of the picture. Near, right? Whatever. That's.
Wait, that not R infinity.
This is R equals 3.5 whatever. 3.57. It's right there. This is 3.57. Right there. And then it starts filling in, looks like filling in densely, because it's not periodic anymore.
I thought R infinity was there.
No, R infinity is right here. Everything beyond is chaos. Except for these little windows of regularity within the chaotic sea. There are islands of normality in the chaotic sea. Right? But this is the picture. This is what you get. Like it or leave it, this is what you get. This was a shock, of course. Yeah.
באזורים של הכאוס, יש, נגיד ל-R ספציפי יש אינסוף כאילו נקודות, או שזה...
Yeah, well, yes, there are Ein Sof Nekudot, and the question is, I think there are also Ein Sof holes.
Okay.
So it's not like it's uniformly thing, I believe. I could be wrong, but I think.
עוד שאלה?
Yeah.
אם יש לך נגיד תנאי התחלה כלשהם, שעבור נגיד, לא יודע, X קטן מחצי, אז זה נכנס, כאילו זה מתכנס לתוך כזה...
No, there aren't bases, no. This phase space is so simple that it's simply connected. Everything, all initial conditions are equivalent.
Okay.
There are no, except for exactly at a fixed point, but, modulo that.
לא בסדר.
Yeah.
Do we know the lower bound?
No, we know nothing.
לא, כאילו על האזור הלבן.
Yeah, I don't think so. I don't believe so. I mean, not that I don't know it. Maybe you know it, but I don't know it.
What's the difference between the two graphics?
That's. I think this is. Yeah, I think this is for. This is. Yes, this is for a different map. This is for a different map. So, I think this is the right picture.
The second not correct.
It's for a different map. And the point being that if you do it for a different map, you get the same picture, roughly speaking. The numbers are all changed to protect the innocent, right? The X scale is completely different, but you see the picture is the same picture. I mean,
So there's
qualitatively
something
speaking,
behind it.
there's some deep things behind us.
We will see what is the deep state.
Well, I mean, we will hear about some of it. We will learn. We will prove some of it, and we'll hear about the proofs of other things that we don't know how to prove. That I don't know how to prove. That they can be proven by people far wiser than I. All right.
What do you write before 2 and 3?
What do you mean?
Upper.
And one is one.
1.
Right. That's the birth of the non-trivial period 1 state is at 1. Okay. Now. So, what the question is? What is next? Okay. And okay, we did that. We did that. Yes. Okay. Next thing that we want to talk about is is the Lyapunov exponent, which we mentioned in the context of the Lorentz attractor, the property of chaos that things become that they point in different initial conditions spread out. That's true here too, and you can measure it with this Lyapunov exponent. And here you can actually, you can actually write some formula down because everything is so simple. Because you can take derivatives, which you couldn't do in the. Okay, so the Lyapunov exponent is defined to be okay, 1 over n log delta n over delta naught. In other words, you start out with 2 trajectories, one starting at some x, and the other, which is okay, and the other starting at x plus delta naught, right? And then you see how you calculate the difference of them. That gives you delta n, right? And you look at how, so if you start out with delta naught being 10 to the minus 6, then you see how delta naught changes in time, how delta changes in step number, which is time n, right? And if it's growing exponentially, then what you want to calculate is the log of the ratio. That gives you the factor it grew by, right? And then because it's supposed to grow by the same factor more or less each time.
Why you wrote it in a line? Just because it's exponential.
Right, so if it's exponential, if you want the exponent, the way to isolate the exponents, take the line, right? And since if it went like e to the nt, e to the alpha lambda n.
You want the difference in the.
Right, so you take n, the limit n, you take n goes to infinity, the limit n goes to infinity, delta naught goes to 0, right, of that thing. And that is the Lyapunov exponent. Okay, now, however, we know that delta n we can calculate by looking at the iterates of the map, right? So, in fact, this is one limit, whatever, of 1 over n ln of fn, the nth composition.
Why do you divide by delta 0?
Because it's supposed to grow by a factor. Right? I picked delta naught to be 10 to the minus 6, and then it goes to 10, 5 times 10 to the minus 6, and then it's 2
Yeah,
to the
by a
5.
factor of some amplitude or something.
Right, so you don't care about the initial amplitude, except it better be small, right?
Yeah.
Because otherwise, at some point, it can't be, the difference between the points can't be bigger than 1 because the whole thing is on the range, right? So you look at Fn of x naught plus, what do I want to say? Yes, it's basically log of Fn prime of x naught is, yes, Fn prime of x naught, where this is Fn, F composed with F n times, which we're going to write as Fn, the nth iterative, right? Because delta n is, I move the initial condition, the way I can calculate delta n is with the nth iterate in one step, so it's the derivative with respect to x naught of the nth iterate, right? And I still have to take the limit n goes to infinity of this thing, right? And now, and
delta 0 goes to the 0?
well, no, that's why you get a derivative,
Ah.
right? That's how I got a derivative, because it's all proportional. The shift is proportional to delta naught.
I not understand what you write.
What?
Delta
Goes to 0.
Ah, okay.
Right. And now this is, because we saw how you take derivatives of this is, in fact, the ln 1 over n ln the product of f prime of x naught, f prime of x1, f prime of x2, blah, 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 blah. Like that, right? Because remember, when you take the derivative, when we took the derivative of the second thing, we got f prime of p times f prime of q, right? That was so therefore the obvious generalization of that is you get f prime of x naught, f prime of f of x naught, which is x1, f prime times f prime of x of f of x2, 1, which is x2, blah, blah, blah. So you get that, right? So this is a product over all those things, but the ln of a product is a sum. So this is 1 over n times the sum of the lns of f prime of xk. Sum 1k. All right? And of course, we want to take absolute values because if it's negative, we don't want pi's floating around. We're only interested in the magnitude of this thing, right? We're only interested in the magnitude, not the sign, because we're not interested in that. And this is the Lyapunov exponent, right? And so, in fact, you can compute this by just picking a point and just keep iterating it and iterating it, iterating, and take the sum. And when you do that, you get the following lovely graph. This is Lyapunov exponent as a function of r. So it is, the Lyapunov exponent is 0 at 3 because it's marginally stable at 3, right? Then it's stable, right? So lambda is negative. It goes down to minus, it goes down to 0, minus infinity because it's log of 0, so it goes down to minus infinity.
Wait, the product is to infinity? The sum is...
Yeah, the sum is to infinity, right? In principle, practice, you cut it off after a million.
N and you take the limits.
Right, so this is 1 over, this is now n, and this is n.
And you need to take n to infinity.
Right. But it's enough to take, in practice, you take it to a million and you're happy with yourself.
Yeah.
Right? So anyway, what happens is it's stable. This is the period 2 solution. It's stable, stable, stable. It's super stable at this value where p equals 0. Right? And then it becomes less and less stable because now it's negative. Lambda is, the factor is negative. So now it's becoming closer to minus 1. Here it hits minus 1, and therefore it's now marginally stable again. That's the birth of the period 4 solution. then it goes down to minus infinity, right? And when it's super stable, and then it comes back up to 1, and that's where it comes back up to 1 is the period, birth of the period 4 or 8, I forgot where I was, yeah, right? And then the same thing happens, it goes down, does that an infinite amount of times, and here you see, you can't see it because, I mean, the resolution is finite, but at some point it becomes positive. That is at R infinity, that is the birth of chaos. The sign of chaos is a positive Lyapunov exponent. And that happens exactly at R infinity plus epsilon, is when it crosses for the last time, it crosses positive. And then, of course, when you get, there are other things that happen. There are these regular windows where it dips negative, but generally speaking, for almost all values of R, you have chaos, except for these little windows of...
If it's negative?
That means it's stable. So these little nice windows we saw, right? These windows of regularity, here for these values of R, lambda is negative. Because you have a stable...
What is lambda present?
It's the stability of you have a trajectory. You ask a question. I have a trajectory, a point, bum, bum, bum. Now I change this infinitesimally, right? And I want to know, will the final answer converge to the original answer when it's small, or will it get further and further apart? If it gets closer and closer together, for example, if I'm on a period 4 trajectory, right, I'm getting closer and closer because I know where I'm going to wind up, and that's independent of anything.
So when it's negative, it's less than
it's
1,
converging,
so
right? It's it's less
and
than
it's divergent when it's bigger than 0,
right?
And it's bumping when it's equal to 0.
No. The trajectory is bumping. If the trajectory is periodic, a period 4, say, right? All initial conditions go to that trajectory, right? All initial conditions go to that trajectory. And therefore, that trajectory is stable. And therefore, lambda is negative, right? Because if I start out with 2 points that are close together, they have to wind up on the same exact trajectory. So therefore, the difference is 0.
I'm talking about the bumping case, when it bumps between 2 values.
Yes,
for example.
that's what I'm saying. That is a stable thing. That is like a limit cycle. That's like a stable object. Though it hits those 4 values of x's and no others, or those 8 values of x's and no others, and therefore the difference between different initial conditions vanishes because I have to wind up at the same exact place. One of those 4 numbers.
What is the value of lambda?
Negative.
Negative.
Which means it's stable. Negative lambda means the differences go to 0 as I go further and further.
And when it's bigger than 0,
then it's unstable. That means it's chaotic. That means that you forget where you wander, where you wind up has nothing, is 2 people who start up right together, right next to each other, wind up far apart. That's sensitive dependence on initial conditions. That's the definition of chaos. Yes.
And let's say that I want to go backwards, right? I'm in a 16-period solution, and I want, by decreasing epsilon, to go back. I can only go back before I cross to infinity, right? Or you cannot.
What? I mean, what do you mean? You can always change R to be whatever you want. I don't know what you. If you're in the. I don't understand exactly what you're trying to ask. No.
Can we do a process of oscillations that we are decreasing the number of?
Yeah, if you change R the other direction, then yeah, you'll go from a period 8 to a period 4.
Slowly.
Yeah, you'll go to a period 4.
Okay. Right.
So the minute you cross that boundary, you wind up on a period 4. There's a transient to get there. I mean, you have to, but you'll get there.
Right.
Okay. So now, all right. So there are, the fact that these two pictures look alike is not an accident. And in fact, we said that in this thing there was a period 5 solution, a period 6 solution, and a period 5 solution. I think that 1, 2, 3, 4, 5, 6. Yeah, this is a 5. 1, 2, 3, 4, 5. This is the period 3 solution. Right? That is, in fact, universal. Every map goes through the exact same sequence.
Always 6, 5, 3.
Yes, always. And then there's an infinite sequence of windows, and that sequence is always the same for all maps which sort of look like the logistic map. In other words, they're on a finite interval and they have a single quadratic peak. And all maps behave the same way. Now that's already becomes like, like mystical stuff. I don't know how to prove that, but a famous guy named Metropolis proved it. I have absolutely no idea how you proved it. He proved that the sequence of what kinds of periodic orbits you get is exactly the same. For all maps that look like that. Whether it's sine or sine squared or whatever, or with the logistic map or
convex function.
Any convex, any single period has a single quadratic maximum. A single quadratic maximum. Yeah.
And if the maximum is like
quartic?
which root?
What? Right, then you get a different sequence. Right? But all ones with a quadratic quartic peak have the same sequence. What? It's a quadratic peak, right? The derivative, right? What's that here it looks at the peak it looks like a minus b x minus x star squared, right? It's got to not arba, right? With something else. Okay, so that's amazing. But what really set the world afire when I was young and innocent, and was we had this list of R's, which I had probably gotten rid of. Yes, right. I wrote down this list of R's, and we saw that we saw they were converging to R infinity. The way they converge, i.e., you can define, if you Rn minus Rn minus 1 divided by Rn plus 1 minus Rn, right? That number is universal. For all maps that look like that, this is the same. The limits, when n goes to infinity of this thing, is the same number. That was proven by a man named Mitchell Feigenbaum. And that set the world on fire. I mean, people were just in total shock. Just total shock. And not only that, I mean, so there were a whole bunch of other things that he could prove were universal quantities independent of the details of the map. And then people actually did experiments on real physical systems. And they found physical systems which undergo this period doubling cascade. This set of period going from a period 2 solution to a period 4 solution to a period 8 solution, blah, 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 blah. And it turns out that if you're smart and lucky and you play with the system enough so that it basically looks like it has a map, like our Lorentz system looked like it had a map. If it looks like it has a map that looks like this, as opposed to the Lorentz system. Remember, the Lorentz system had a cuspy map like that. So the Lorentz system does not have a period doubling bifurcation cascade. But if you find a system that has a map, so it's sufficiently simple that it's semi-predictable like that, and the map sort of looks like this, the details don't matter, and this number is the right number. And so they actually measured it in a system of, they took a bath of mercury and they heated it up from the bottom, and you get convection rolls, and then you heat it up a little more, and then the convection rolls start oscillating, and whatever. And I think I have that picture.
Wait, so
they came with
what you say that is a universal number for something?
This the way
quadratic,
the
right?
parameter. This is the parameter controlling the system, R,
Yeah.
right? Which is the temperature. And then you look at where the onset of the period 2 is, and then where the onset of the period 4 is, where the onset of the period 8 is. And construct, and those you call R1 period, R2, R3, R4. R4 for the 16, where the 16 is born, R5 for the 32,
Yes.
blah, blah, blah. You calculate these ratios, and you look where they're going. Right? Now, in practice, you can't go to infinity you look at this thing for n equals 1, 2, 3, 4, and maybe 5, right? And you hope that's infinity. You look at those numbers, you see where they're going to, and lo and behold, with an experimental error, they go to the number that Mr. Feigenbaum calculated, which is this universal number. So here's a period doubling cascade from an actual experiment, physical review letters. This is a period 1 thing. You see the maximum temperature at each period is the same. And then you change the thing and you get up, down, up, down, up, down, up, down, up, down, up, down. That's a period 2. And then you go to here and you get up, down, up, down, up. So this is higher now than this. So you go up, down, really down, up, down, really up, really down, up, down, really up, really down, so forth and so on. That's a period 4. Then you increase the parameter some more and you get up, down, more down, less, medium up, medium down. That's a period 8, right? And he got to 16, and then he, like I said, that's enough. And he calculated these ratios, and lo and behold, within 10%, he got the number that Mr. Feigenbaum had calculated. And everybody was like, that was amazing. And that was the high point of chaos. And what it means to be the high point is that was the moment the chaos started decaying, because that was the pinnacle of the achievement in chaos, is that you were able to actually construct a physical system which had a simple enough dynamics that it looked like a map, and it had the right behavior. Now,
and then chaos and.
Because the problem is that most systems have what's called high-dimensional chaos. They don't have any nice map associated with them. It's only very special systems which you have to work really hard to create. But if you look at the weather, I mean, it's like it's a huge dimensional system, and there's no nice simple maps or anything like that. No, forget it. So for most practical systems, knowing that it's chaotic doesn't get you very far. Here, it got you amazingly that you were able to uncover this piece of knowledge that you would never have guessed going into the game. That this would be the case, that there would be some universal law about when these transitions occur, right?
And there is no any generalization for that in more than one.
No. This was the high point and the death point, the beginning of the end of chaos, because
the quadratic term in the
right. Yeah, I mean, and then so I mean, it was a tremendous. I mean, it just impressed the hell out of everybody.
They're supposed to reach up again. So,
but the fact that Feigenbaum didn't win a Nobel Prize, it's actually, I mean, he might, I'm sure he must have been nominated for a Nobel Prize in physics for this. I mean, but the fact that he didn't win one is because at some point, I guess, I don't know, but that's the story. It was an amazing achievement, but it led. This is where it led, and basically for no further in terms of. So there's a story of how to calculate this number. I mean, Feigenbaum had a theory of how to calculate that number, And let's see. I think it's I think it's better off to do it. Let's see. Can I do it in 15
What
minutes?
is the number?
What is the number? I have it written down somewhere. And if I, where is it? I wrote it down.
How
I
did
think.
they came with the experiment? Like they no turn no apart.
I didn't write it down, of course.
I
I know I wrote it down. I think I left the paper behind. I had.
I think it's like 4.66, something like that.
I wrote the other number down. There's another number, which is in this diagram, in the xn versus x versus r diagram. If you do the following exercise, this is another universal number. You go to xm, which is the point of the maximum of the map. So for the logistic map, that's a half. Right? And then you have the bifurcation here. And then you have the and so you define, yes. Right, so at the point of, at the superstable point, you define this distance as dn, and then you go to the next one, and then there's another bifurcation which hits this thing, and you define this to be dn plus 1, and so forth and so on. You look at how the different the size of the orbits basically, and how they converge, and they first of all. They have a minus sign because this one is up from that, and this one is down from that, and whatever. And there you get a number which is 2.5029, or something for ratios, minus 2.5029 for that. And this I forgot.
Written here in Google, it's 4.66.
Yeah, 4.66 something or other, right?
669.
Right. So next time we'll talk a bit about how to derive that, because that's a story in and of itself. But that, and then with that we'll end chaos, and then the rest of the time we'll move on to partial differential equations and the dynamics of partial differential equations and bifurcations in partial differential equations, which is and how that gives rise to patterns and all kinds of lovely things. So, yeah, so that's the agenda, is that we'll start next time, we'll present some parts of this renormalization theory, and then we'll close the book on chaos and move to PDEs and talk about the Turing instability. It's named after Alan Turing, the guy who invented the computer, among other things.
שבוע הבאים זה יום בחירות, אחר כך זה קצת בדיונים, עוד לא התחלנו, נעדכן במייל.
ותרגיל בית.
תהיה השלמה או משהו? אני לא יודע איך זה עובד.
לבחירות?
כן,
לא, בעיקרון לא.
לא, אוקיי, מצוין. אני גם תרגל, אז רציתי לדעת אם אני צריך להשלים.
היה לך את השבוע ההשלמה אבל של המילואימניקים.
כן, שמשום מה לא קראו לאף מתרגל מהקורס שאני תרגלתי, אז כאילו...
ירדן זה במייל שלך לחפש.
לא. אולי קראו למתרגל אחר, לא לי. יש כמה מתרגלים בקורס.
טוב. So yes, next week is the election day, so no lecture. And after that, send the emails. No, we need to. Maybe it will be another one exercise.
This week, another one?
Yes, and we'll need to invite all of you to solve us some problem from the homework.
On the lecture.
So this is
You
what
will
we
tell
do
us
in the
which
side.
problem from the homework?
Huh?
You will tell us which problem from the homework we'll need to
No
solve?
advance.
Huh?
Not in advance.
By the way,
yes.
you know computation, נגיד בעברית, רקע תכנותי לא היה בקדמים של הקורס, ובשיעורי בית יש קצת תכנות, כדי קצת לעשות בולי לחבר'ה כמוני שפחות טובים בלתכנת.
שלא יודעים לתכנת.
You can Google it. Like every code is...
אני יודע שאני יכול להשתמש ב-GPT והרבה כאלה, אבל אני רוצה...
לא, נראה לי ש-GPT לא יצייר.
כן. כאילו, אם זה בונוס אז בסדר, אבל כאילו זה כל פעם, אני לא מתכנת טוב, אני לא...
אני גם לא.
זה לא בדרישות קדם של הקורס, את מבינה מה אני אומר? אז כאילו...
MATLAB, it's not a part of the...
לא?
No.
אני לא למדתי MATLAB באף שלב בתואר.
When I did the course, MATLAB was one of the...
אוקיי, so...
previous.
באמת קראת את הסילבוס אבל? זה מה שאתה מפתיע אותי.
כן?
אני קורא את הסילבוס של קורסים.
I also did it.
רואים שהיכל מתרגלת, ובאים.
Okay. So tutorial number 8. So until now we talked about non-linear systems in 2 dimensions, right? And we saw some behaviors and things that in a big picture we can somehow solve it. Okay? When we are going up to 3 and more dimensions, things start to be more complicated. And for example, we saw in Poincaré-Benedict theorem that if we are in 2 dimensions and we have some trajectory in a bounded area, it will, at the end, it will close itself, okay, to some closed trajectory. Okay, but in 3 dimensions, you saw the Lorentz equations, right? That did something like that, right?
Mm-hmm.
And this is also in some bounded area, but there is no closed loop in the thing. So what are we going to talk about is 1-dimensional maps. Okay, this is some tool that can help us to solve problems. Okay, so what are we talking about? We have some recursivity.
Recursive relation.
Yeah. Of xn plus 1 equal to some function of x of n. Okay? Recursive relation. And we want to solve this system in a similar way that we solved the 2-dimensional. Okay? The 2-dimensional system. In this actually we have the same thing, but what is the word? Continuous. Okay, we had a continuous map. Okay, this is called the map, and when we had 2-dimensional, we had a continuous. So what we want to do, we want, in fact, to find also in this case the fixed point. Okay, where x star will be equal to f of x star. Okay, so how can we do that? We start with define we define a step, okay, xn, that will be equal to x star plus the step, okay, at n. That means, let's write, if we have x star plus eta n plus 1, this is x n plus 1, right? And this is actually f of xn, and this is f of x star plus eta n. right? Let's open it with Fourier. We get f of x star plus f prime of x star dot eta n plus higher orders of eta n, right? Okay, now we suggest that eta n is a small step, okay, that the initial condition is close to the fixed point, so we can neglect this term and we get the equation on eta n, that eta n plus 1. Remember that this is actually equal to x star, right, because this is the fixed point. So we get eta n plus 1 is f prime of x star dot eta n. Okay, and this has the solution is eta n is f prime of x star by n eta 0, and this we can define as lambda, okay, where lambda is the f prime of x star, okay. Okay, so now we want to, if we have a fixed point, we want to, yes.
Maybe you can change the push.
Yes. Thanks. Okay, so I want to classify the stability of the fixed point. Okay, so we have the options of, we have 4 options. Okay, absolute value of lambda equals 0. We get super stable fixed point. Lower than 1, we get stable fixed point. Equal to 1, this is undetermined fixed point. Okay, we cannot know what it will be, and lower than 1,
Bigger.
Bigger, yeah, thank you. Unstable fixed point. Okay, what is super stable? It just means that it, yes, it is faster. Okay, what can we do in this case? How can we say if the fixed point is stable or unstable? We'll do it graphically, okay? We will start first, let's call it x and y, okay? We start first with drawing the line of f of x, okay? And the second will be the line y equal x, okay? What are we doing? We start in some x0, okay? We're going on x0. We're going to fx and got the next value, okay, of this step. What is the step after x0?
X1.
Exactly, x1. Okay, this is the next step. So we are going to the next step on x1. Okay, we started here, moving here, and now we are in this point. Okay, we are going on x1. What is the next value? It will be x2, right? And then we continue until we are going to some point that we can see if we are going to the point or out of this. Okay, this is called cobweb diagram. Okay, and this is the method that we will use. Okay, questions until now? Okay, great. So, exercise. Okay, 1. Okay. Analyze the map xn plus 1 equals 2xn over 1 plus xn for both positive and negative xn. Okay, so how are we starting? We start with define fx, of course, right, to be 2x over 1 plus x. And now let's find the fixed point. So we want x to be equal to x over 1 plus x. So we have 1 plus x minus 2 equals 0. We have first x star equals 0 and x star equals 1. Okay, two fixed points. Okay.
Change fx to x.
We want to find the fixed point. Where this. Okay, so let's classify them. F prime of x is 2, 1 plus x minus 2x over 1 plus x squared. This is 2 over 1 plus x squared. Right?
Always positive.
It is positive, but we care also about 1. Yes, about the absolute value. Okay, so f prime at 0, this is 2, right? Bigger than 1. Okay, that means that this is from there, if it is unstable, and f prime of 1, where am I here? 2 over 4. This is lower than 1, that means great. Okay. Okay, so now we want to draw the web, so let's start with drawing the function itself.
That only means that if you start close enough, it's stable. You can still start very far and escape to infinity or minus. Because we used an approximation for small eta.
Yes, yes.
Wait, no. I think if you start at infinity, it will be just function f of x equal to 2 or something like that.
Right, in general, not specific.
Okay.
Okay, so the function looks like this. Okay, this is minus 1. This is x and x. And okay, if you want to, let's go more like this, would be more easy. No. Okay, I hope it is big enough. We draw fx, and this is a line, y equal x. Okay? So let's draw the cobweb.
No, close to 0 is approximately 2x, so it's going to be that y equal to 2x.
so if you're starting from a positive point, okay, let's say that we start here in some point, okay, we are going up. This is the value, so we're going right to the value on the line y equal x, up, 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 until we get this point, okay, the point of 1, stable. And if we're starting in the left, so if we start in this area, okay, we are going here, doing this, going up, da 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 da. No, sorry.
You need to continue by called X line.
And this is y equal x. Okay, we're starting here. We are going down. Okay, we are going down, we are going to this point. This point to where it will be catch and go away. Okay, and if we start like here, so we are going to this point, and from here we are going to here. Okay, and again
It's still, you still have,
reach the one.
you have the point there. It's also it's supposed to go up.
Where?
The point about a little bit less in minus 1.1-ish.
Here?
Let to go down. This point goes supposed to go up, not down.
This point.
Goes up to the function, not down. Down is there no function. Down.
You're right. Okay, but again, okay, we are going up and continue to this point. Okay, cool. And what will happen if we're starting here? We are going back, and from here down to the line left, and we are going to the point. Okay, so this is the cobweb. Okay. Next. Okay. Consider quadratic map xn plus 1 equal xn squared plus c. A. Find and classify all the fixed points as a function of c. B. Find the values of c at which fixed point okay, and classify those bifurcations. C. For which values of C is dark stable to cycle when is it super stable, and D. locate the fixed point, the two cycles, and their stability. Okay. Great. Okay, so for the system xn plus 1 equal xn squared plus c, let's start with A. Find and classify all the fixed points as a function of c. Okay, so fixed point, how we start, again, fx equal to x squared plus c. Okay, we want to find the fixed point, so let's equal it to x, and we get x12 is minus 1 plus minus squared 1 minus 4c over 2. Right? Okay. So when it will be appear? Only when. Great. C, no, bigger. Bigger than. Bigger? No. Wait.
You need to stay to be positive.
Yes. Okay. C lower than water. Okay. Let's classify them. F prime of x is to x, right? So F prime for, let's start with the plus. Okay? This
Minus
is
always negative.
I'm sorry, this is plus. Yes. So here we have 1 plus something over 2. I'm sorry. Okay, no, yes, dot 2. Okay, the derivative. 1 plus something, this is always bigger than 1, right? So that means, I erase that, never mind, bigger than 1, it is unstable.
Your left. Your left.
Ah, great. So this is unstable. Okay, now what for the minus point?
C is positive.
C, it is appear only when C is lower than water, so not sure. Like maybe yes, maybe no. Okay, what is this? Is 1 minus the square root, right? Okay, now we need to find when, like, all this happens. So let's see, when it will be equal to, okay, let's do it like this. Lambda equals 0, okay, when it will be, yes, if C is 0. Okay, if C is 0, so we get super stable. If lambda lower than 1. So let's start with equal 1. It is more easy. This is when C equal water and minus 3/4. Right? This we get undetermined. We will need to solve it. Lambda lower than 1, we get between quarter and minus 3/4. Okay, and this is stable. And lower than 1, we will get for C lower than it. And this is unstable. Okay? Okay. Okay, find the values of C at which fixed point bifurcate and classify those bifurcations. So let's say this. Okay, that it will stay here. Okay, so let's start with drawing the bifurcation diagram. Okay, we have C and E. So how it looks like, it is something like this. Okay, when let's see equal to water, we got one stable and one unstable, right? Where we are. No, okay, this will be every time unstable. Okay, and now in this area we start with stable, okay, until we get to -3 quarters, right? So the bifurcation diagram looks like this. Okay. Okay, in this point, this is something that we saw, right? Which bifurcation is it?
Saddle.
Great, saddle. Saddle bifurcation. And in this point, no, it is a flip. Okay, flip bifurcation.
We didn't have flip in just.
Yes, so we saw it now and we will understand it better in the next section. Where we are, C. For which values of C is there a stable to cycle? When is it super stable? Okay. So what is it to cycle? To cycle, it means when we have some two values, okay, of P and Q, that the function jump between them. Okay, that means that P is f of Q and Q is f of P. Okay, this is two cycles. So when we have it, okay. Some note. This thing you can also, of course, write as f of B is B, and f of Q is Q. And this is second iterate math. Okay, it is defined as f squared, but f squared is f of f. Okay, some note. Okay, so we want to find those f and p and q. Sorry. So what we want that p squared plus c equal q, and q squared plus c equal p. Right? Okay. Okay. So let's subtract the equations, and we get p squared minus q squared. This is p plus q, p minus q. This is equal to minus p minus q. Okay? It is this minus this. Okay, p is not equal to q, right? Because we define it as 2 points. Okay, because we want 2 cycles and not one. One is just fixed point. So we can do that, and we have p plus q equal minus 1. Okay, let's take it and put it inside. So we have p squared plus c equal q. Q is minus p plus 1. Right? So from here we can get p equal minus 1 plus minus square root of 1 minus 4c plus 1 over 2, and q will be minus 1 minus plus this thing over 2. Okay? Okay, due to the symmetry, we can just choose p to be the plus and q the minus, right? The symmetry. It can be also the second. And okay, that means that p is minus 1 plus minus 3 minus 4c over 2, and q is minus 1 minus 3 minus 4c over 2. When it will appear? When minus 3 minus 4c will be bigger than 0. That means c is lower than minus 3 factors. Okay? Spoiler, this is what happened here. Okay? So this is when it appears. Okay. Okay, is it stable? Let's see. Okay. Okay. So we define the function in this way, right? So let's write the derivative of that. So we have f of x. Okay, let's start with that. F of x. What is equal to? This is x squared plus c squared plus c. Right? This is x squared plus 2cx squared plus c squared plus c. Okay? Derivate it and we get f of x 1, 2, 3 prime is 4x third plus 4cx. Okay? Let's put inside b, f of b prime. This is 4, where is it? Here. Okay, let's say it's 4p, right? Like p squared plus c, right? Okay, what is this? This is actually 4p, p squared plus c, this is q, right? So it's 4pq. So now, are you agree with me that this is actually this also? Great, so that means that their stability will be the same, okay? There is symmetry in the system. Okay, what is equal to? This is 4, this, but this is actually minus, this is, okay, 1 minus 1 minus 4, I have it here. 1 minus 3 minus 4c over 4. Let's take it out. So we have, this is 4 plus 4c. Right? Okay. So what are the cases now? We have this. Okay. So this is to be 0. It will happen if, wait, Okay, they're using some problem, but okay. Lambda equals 0. When it will be at C equal -1, right? This will be super stable. Lambda equal 1. When it will be if C equal -3/4 or -5/4, right? Lambda bigger than 1, it will be if C is lower, and bigger than 1 if it is between them. -5 and -3/4. Okay.
If lambda is bigger than error, the fourth line.
This
Lambda
one?
is
Bigger than 1, I think.
bigger than 1.
No.
Bigger. Wait.
The one above is smaller than 1. Yeah. Smaller than 1 and bigger than 1.
This is bigger, this is lower.
Than 1.
Yes. Let's see if we put it here -2. So yes. Okay. Okay, so we have all the stabilities. Okay.
סליחה, אני קשור לקבוצת מנטרות.
כן?
קבוצת מנטרות, נראה
Okay, what we need to do, plot a partial bifurcation diagram for the map. Then indicate the fixed point, the two cycle, and their stabilities. Okay, so we want to draw everything. Okay, so ta-da-da. Okay. Let's start with the diagram that we have. No, let's start with the new one. We have C, okay, and let's call it fixed point. Okay, all of them will be here. So let's start with P and Q. Okay, P and Q looks like this. Okay, when this point is at -3/4, okay, and at -5 we change the stability. Okay, this is P. P, we said that it is always unstable, right? So this from here to the end, this is the P area, and this area is of Q. Okay, and now the area of the X star plus and minus, we had it from before. Okay, we have this thing. From here we have the unstable area, and also from here. Okay, so actually this point became a, we have it here also the flip bifurcation, okay, but also the P and Q that's called period doubling bifurcations. Okay. Where we did it, I think I erased that. But when we get this point, okay, in this point we have the f prime here was -1. Okay? And this is a clue that this bifurcation will also will come. Okay, questions? Okay, so we finish.
קטע אבל שאנחנו כאילו רוצים תמיד כאילו שאנחנו, בוא הרי זה כאילו נגיד